Okay, what concept in calculus have we not incorporated into our motion unit? Antiderivatives. That's what we're basically going to do today. How do antiderivatives fall into this concept of motion? Is Jake not here today?
No.
Is he not coming?
Maybe. There's a big back up on 370.
There's a big question mark for me here in a minute.
All right, so we know that velocity is the derivative of position, and acceleration is the derivative of velocity, or the second derivative of position. So what if we know velocity and we want, just kind of gave it away there. What if we have velocity and we want position? What are we going to have to do?
DT.
Let's try that again. What do you say? Antiderivative with respect to t. Okay. What if we have acceleration and we want velocity? We need to take the antiderivative. Okay. Now, you know that when we take an antiderivative, we get that plus c if it is an indefinite integral. Okay. So if we want to know the exact equation for position, given velocity, or if we want to know the exact equation for velocity, given acceleration, then we at least have to have one piece of data plus to find c. Okay? So that's what we are going to work with first. Okay? We know that the position of a particle has velocity, write this down, cosine of pi t. And the position is 4 when time is 0. Write at least those two pieces of information down. Okay, so Larry, what's the first thing we need to do in this problem if we want to figure out the position function?
Take the antiderivative of that.
Okay, so we know our position is going to be the antiderivative of velocity. All right, so Joe, what's the antiderivative of the cosine of pi t?
Sine.
How do you feel about that? Antiderivative of cosine is sine. We have to take into account that chain rule with the coefficient in front of t. So 1 over pi sine of pi t plus c. All right, now they gave us some information about a particular position at time equals 0. All right, so we're going to need to plug that in to be able to figure out what that plus c is. So we have a position of 4 when time is 0. What's the sign of 0? 0. So our C value is 4. So we've solved for C. We can plug it back into our position function. Our position function is 1 over pi sine of pi t plus 4. Next, what happens if I give you an acceleration function and I want to know the position function? Okay, so we have that our acceleration function is 3t squared plus 2t. If we need to get all the way to the position function, not only do we need to know a data value from the position, but we also need a data value from velocity. Okay, basically we're going to have to do the same thing we did on our last example, but twice. We're going to have to go from acceleration to velocity, solve for that C, and then velocity to position.
Yes.
So our velocity is just going to be the antiderivative of acceleration. Michael, what's the antiderivative of 3t squared plus t?
T cubed plus T squared plus C.
Excellent. What data point do we plug in? Which data point do we plug in to solve for C? Awesome. 3, 2. When time is 3, our velocity is 2. What does that make C? Negative 34? Double checking.
He's right.
Okay. Great. So our velocity is t cubed plus t squared minus 34. All right. Now I would like you to go from velocity to position. You take the antiderivative of velocity, then use the data point 3/8 to solve for that constant. 1, 2, 3, go.
This moment, 2 days and counting.
Exciting. It's not the most, it's not the nicest of constants.
3.75.
see that Tony Romo's retired. Yeah, he is.
Really?
He's taking an analysis. He's taking like an analyst job at ESPN or CBS. Yeah. Right before he was about to get a ring too.
I'm trying to play highlights.
Yeah.
I think it's talking about Tony Romo.
I know. There's Tony Romo's the greatest to ever play. He turned Dallas into what it is today. No. Pin it down with Tony.
All right, Cole Smith, what's your position function?
1/4 T4 plus 1/3 T cubed minus 34T plus 323/4.
Which could, as a decimal, is 80.75. Okay, either way would be acceptable, whether it's a fraction or decimal. All right. We need to talk about the difference between displacement and distance. Okay. Displacement is the resulting position of a particle after a certain time period. Okay? So if I am right now standing at the origin and I walk 3 feet to your right and then 4 feet left and then 1 foot right, I'm back to where I was started, correct? My displacement is 0 because I'm back to my starting position. Okay. So, if it correlates to, where you were to begin with, then if you have a negative displacement, then the particle is to the left. Okay. If you have a positive displacement, your particle is going to end on the right. Okay. Similar to kind of what we were working with yesterday. And as I demonstrated, if your displacement is 0, then you're back to the original position. Okay, so wherever you start, the displacement refers to where you are from that point. Okay, so what I'd like you to do is talk about, okay, I have this graph up here for a reason, right? If this were to be a velocity graph, how would that relate to finding the displacement of a particle? Have a 30-second conversation. All right, what do we think? You had your hand up? No? Well, I'll still call it you guys anyway. Pod 2, what do you think? How do you find displacement if I give you velocity?
Out of the areas.
Okay, and adding up area under the curve is the same thing as doing 1. Okay, so if we want to find displacement, we're going to take the integral of velocity on an interval. If we took the integral of this velocity graph from A to D, it would tell us the displacement from A to D. Okay, so this is the example we're going to do regarding displacement. Okay, I'm giving you the velocity is t squared minus 2t meters per second, and I want to know the displacement over the interval 0 to 3. Okay. So all we have to do for displacement is take the definite integral of velocity over the interval that has been given to us. All right, so Josh, what's our antiderivative for this?
This one is t squared.
Oh, no. Sorry, Josh. I wrote it down wrong. It's t squared minus 2t. So let's start over. Let's try this again. Good. And then we have to evaluate this from 0 to 3. Thank you for catching that, Jake.
Good job, Jake.
All right. So we have 1/3 times 3 cubed minus 3 squared minus 1/3 times 0 cubed minus 0 squared. What is it?
0.
We have a displacement of 0. Which means what? Did this particle not move at all?
No, it moved, but it just ended back up at the origin.
Okay, so we're back to the original position. Now, this doesn't necessarily mean it's back at the origin, okay, because we're talking about velocity. We just know that it's back to where it started, okay? What that position is doesn't really matter right now. We just know it's back to where it started. Okay, now let's talk about my scenario again. See if I can remember it. If I'm right here and I walk 3 steps to the right, and then I walk 4 steps to the left, and then I walk 1 step to the right. What was my displacement?
0.
How far did I walk?
Find it.
I walked 8 steps, didn't I? Okay? I want you to talk about in your group, first of all, why it's the 8 steps. Okay? And what we're going to have to do differently with our integral if we want to know the distance traveled as opposed to the displacement of the particle. So have a conversation with your pod there.
Add them up.
All right, let's talk about ideas. Any thoughts on how this is going to be different than just taking the integral of velocity to find displacement? What did you have to consider with my steps? How did you count them up?
Direction,
What do you mean, Cole?
right, left.
Okay, so even if I was moving in the negative direction, you still counted my steps, correct?
Yeah.
Okay, so how can we apply that to a function, a velocity function? What are we gonna have to do with that velocity function in order to find a distance?
You have time where it's zero, and then take the absolute value of different.
Okay. So Isaac said we're gonna have to take the absolute value of all the different pieces if they're negative, right? Basically what happened is when I walk to the right, those steps were positive anyway. When I walk to the left and I have negative velocity, right? Before those we just like cancel out for our displacement, but if we're counting distance, we actually have to count those steps. So anytime we have negative velocity, instead of those positions canceling out, we're going to actually have to take those into account. So distance is actually going to be the absolute value of velocity. Meaning, that negative area is not going to cancel out with the positive area like it was earlier. We have to count all of that negative area as positive steps. Okay. So Isaac said we would need to find where the velocity is zero. Why would that be important? Why would the velocity being zero be important for this?
When you look from the left and the right to see what's positive and what's negative.
Okay, we have to figure out where is our velocity positive, where is our velocity negative, so we know which ones we need to make positive, right? So you're going to have to find where your velocity is zero to identify any intervals where your velocity is negative. If you have any negative intervals of velocity, then you're going to have to take your integral and you're going to have to break it up into multiple integrals. So if you have two intervals that are positive and one interval that is negative in between, you're going to have three different integrals you're going to have to calculate so that when you find the negative area, you can go ahead and change the sign to positive. This is a concept that's going to come up quite a bit on AP pre-response questions, okay, where you actually have to describe what something means. And you're going to see that tomorrow when we do some practice pre-response questions. But if you see the integral of the absolute value of velocity, you need to describe that that is calculating the total distance that whatever travels. Whether it's a particle, a person, a bicycle, well, probably with a person, but it needs to be described as the total distance traveled, okay? Where if that absolute value is not on the velocity, then it's describing the total displacement. Okay, we need to know the difference. So let's come back to this example here. Okay, we already found that the displacement of this particle was 0. Now I want to know the distance traveled of this particle. Okay. So if we're looking for distance traveled, we have to identify any negative intervals of velocity, which, as Isaac pointed out, we must figure out first where the velocity is 0. What are we going to do with that equation? Okay, so what did you do before that step?
Back to the two.
Okay. So 0 and 2 are the two places where our velocity is 0. So we can make a good old number line. Now, anything over here doesn't matter because we begin at time equals 0. So I'm not even going to worry about that interval. However, between 0 and 2, what kind of velocity would we have? And what kind of velocity would we have after 2? Okay. Since we have broken our velocity up into two different intervals, one that's negative and one that's positive, we're going to need to have two different integrals. Okay? So our distance, okay, we have an integral from 0 to 2 of t squared by 2. And we have an integral from 2 to, we're only going to go to 3, right? This first integral right here, what's going to be true about the area we find under the curve? It's going to be negative. Well, since we are looking for distance, we don't want that to be negative. What would be an easy way to make it positive? Put a negative out in front. Okay, so what we have is negative the quantity 1/3 t cubed minus t squared evaluated from 0 to 2. And then we have 1/3 t cubed plus t squared evaluated from 2 to 3. We have 1/3 times 8 minus 4, and then minus 0, right? Plus 1/3 times 27 plus 9 minus the 1/3 times 8 plus minus 4. All right, what's 8/3 minus 4?
4/3. -4.
Negative 4/3? And so that negative out in front is going to turn that to be positive, right? And then over here, this goes to 0, correct? And then we have minus negative 4/3. So 8/3 meters is actually how far this particle travels as it's going back and forth, right? It may have ended at its original position, but it traveled a distance of 8/3 meters. All right, one more example. Please write down S of t is 2 cosine of t meters, whoa. That should be meters. Okay. I want the position of the particle, its displacement, and given the position, sorry, find its displacement and total distance over the time. Now, I gave you position, didn't I? What do we need in order to find displacement and distance? We need the velocity, okay? So, our velocity curve would really be what? I'm waiting for somebody. Should I call on you instead? Larry, what's our velocity? Two sine t?
Yeah, it's not that.
We're taking the derivative. From position to velocity, we're taking the derivative. So there's no plus c, right? And from the derivative of cosine should be negative sine, correct? Okay, I know, we gotta get all of our patterns straight, right? All right, so now that we have velocity, we can find the displacement. Remember, displacement is just the integral of velocity on our interval. Yes.
I'm sorry, but why is it going to be negative 2 sine? Because if the derivative of sine is cosine, or the antiderivative of cosine is sine.
We're not taking the antiderivative, we're taking the derivative. We have been given the position. And we're going to velocity, so that means derivative. Okay. So we need the integral from 0 to 3 pi over 2. Do you have a question? No, you're good? Okay. Of negative 2 sine of t dt. Here's what makes it nice. What's the antiderivative of negative 2 sine of t? 2 cosine of t. So we have 2 times the cosine of 3 pi over 2 minus 2 times the cosine of 0. What is the cosine of 3 pi over 2? What's the cosine of 0? So our displacement is negative 2. So our displacement is 2 meters to the left. Since it's negative, we're 2 to the left. Now I want to find distance. In order to find distance, we need to take the integral from 0 to 3 pi over 2 of the absolute value of velocity. When we're finding distance, before we actually go to write out our integral or integrals, what do we need to find? Okay, we need where the velocity is 0 so we can determine any negative velocity integrals that we have. So between 0 and 3 pi over 2, where is where is 2 sine of t equal to 0?
Zero.
0 and pi. That's where the sine is equal to 0. Okay. So if we plug in values between 0 and pi, what's true about our velocity? Say louder. It's negative. Between pi and, I mean, really we're ending at 3 pi over 2, right? What kind of velocity would we have? Okay. So we have a negative interval and a positive interval, which means we have to break this up into 2 integrals. From 0 to pi, what kind of velocity did we have? Negative. Since we have negative velocity, we know we're going to get negative area under the curve. We want it to be positive, so we're going to put a negative out in front to cancel it out. Then we'll add the integral from pi to 3 pi over 2. All right, typically I'd have you go through this work. I'm going to go ahead and just tell you that it's 6 meters, okay? We travel a distance of 6 meters, but we end up only 2 meters to the left of where we started. Okay. All right, with our pep rally today, we're a little short on time. We have a pep rally between second and third hour because we're getting an award.
What? Oh, for the.
You guys listen in your advisors.
Well,
Everybody talks, I never hear, like,
Yeah,
I'm
they
just
don't
like,
hear.
shut up, so I can do it.
Okay, so what I want to do in like the last 5 minutes is go over your quiz. So the 3 of you who were not here yesterday, you can take your homework assignment out into the hallway while we go over this.
How well I wrote my first thing in the
That is not very good.